That's on. Is that all right?
That's
I can
good.
mute the sound from here.
That's good. No, that's good. If I just put that there, I reckon.
Yeah, that'd be perfect.
I reckon that's about right. Testing, testing. Yeah, I suppose I'd sit there. Better get on with it. Oh yeah, yeah.
To measure the signal strength of TV distribution.
Oh yeah, that'd be interesting.
Oh
yeah, yeah, yeah.
1 millivolt, which is plus 1 millivolt minus something, fairly close tolerance. And that to make sure that could receive signals from 30 meg to whatever, then you switch to UHF and go another up to 900 meg. I can remember hooking that up to an antenna in the backyard and tracking juveniles.
Thanks everyone. So I'm going to introduce to you Dr. Andrew Klekociuk. Andrew's an old-time member of the AST. We go back many, many years. In fact, Andrew, I can remember you had all the scientific gear going when you were a relatively young man, and I was still quite old for you, I think. But anyway,
I'm not that young.
You had a 6-inch refracted telescope, and you had all this gear on the sun. You were doing stuff on the sun. So Andrew's had a lifelong career in radio astronomy, and as you know, he's the chief climate scientist, I suppose, principal scientist of
Yep.
climate for an RA, and where he's been working for
Too long, 40 years.
40 years. And so Andrew's had a very passionate interest in radio astronomy. So tonight we're going to be very lucky because you know how we always dwell on the optical side of things very much, and not so much on the radio. So it's good to have a change, a wonderful change. So I'll introduce Andrew, who, thank you, Andrew.
Yeah, thanks very much, Rick, and thanks everybody for coming along tonight. Great to see everybody here. I was reflecting tonight, I think it was about 45 years ago, I was actually giving a talk on this very topic to the AST. So I'd like to just enthuse you a little bit in radio astronomy, shift wavelengths. So tonight I'm just going to give you a little bit of history about radio astronomy, and pretty impressive history in Australia, and of course a number of folks here probably have had some connection with various elements of radio astronomy because it's been quite an active area in the university. A few little notes about some radio science basics. I'll even show you an equation or two and some numbers. And then I'll talk a little bit about actually some practical aspects of radio astronomy. I've enjoyed radio astronomy because I can do it any time of the day. Although these days interference is like clouds, so sometimes I just get clouded out by interference. But I've been listening to the Sun, Jupiter, and some other things, but I'm just going to focus in on the solar system tonight. I could talk about other aspects of radio astronomy outside the solar system, but I'll leave that for another time. And then actually how to get into it, how to do something. So just a quick note about the spectrum. You're very familiar with the optical part, but the Earth's atmosphere is transparent to radio waves of certain frequencies, and in fact there's quite a wide window for radio astronomy. That's limited at the lower end here at frequencies of around about sort of 5-10 megahertz by the Earth's ionosphere. That's the ionised layer at about 100 kilometres and above. And I'm mainly going to be focusing in on what I call the low frequency end of the spectrum. So down at these sort of frequencies, generally below about 30 megahertz for my observations from home, down to where the ionosphere limits my observations to some extent. But there's a whole world of high frequency radio astronomy, and of course the university is involved in a lot of that out at the observatory at Cambridge there. So just reminding you, you'll come across some of these names, I'm sure, in your studies, but Karl Jansky, kind of the father of radio astronomy, working for Bell Labs, looking at emissions, natural emissions, and he was measuring galactic emission down at 20 megahertz. That's actually the frequency which is in the shortwave band. So at the time there were a lot of communications around the globe using these frequencies, and Jansky was really the first to make maps, but of course perhaps the best known pioneer of radio astronomy, Grote Reber, back in 1939, made maps at a higher frequency and actually extended the work of Jansky and made more detailed observations. But we're talking at a time when electronics was quite primitive, and in fact it wasn't until 1943 that Reber actually detected the sun as a source and published some results in 1944. He actually probably wasn't the first to observe the sun. That was more folks in the US, that was Southwell, and in England, Hay, but they'd actually been observing the sun during the war but couldn't publish their results due to wartime limitations. It was a few years later that other emissions in the solar system were detected, and that was by Bernard Burke and Kenneth Franklin in the US, seeing that Jupiter was a source of radio emissions that varied in intensity. So you can see all of this is relatively recent past. I'm not old enough to remember some of these things, but when I started out radio astronomy, it wasn't many years before that all of these observations were made. And just going on into perhaps the more modern time, back in 45, again, post-war times, when Australian radio astronomy really started off with Joseph Pawsey and also Ruby Payne Scott and Lindsay McCready making measurements of the sun. It actually pioneered a lot of work on the sun, saying that sunspots are actually a source of radio waves, things we take for granted now that really nobody at the time had any idea about. They were using a radar system on the cliffs in Sydney and using an interferometry technique, so interference fringes that told them where the source of the radio waves was. And then after that, radio astronomy really took off in Australia. CSIRO had a big presence, and of course the University of Tasmania, who in the late 50s established a strong presence in radio astronomy, which continues today. But I won't go too far into the future, and I'll go back actually to terrestrial radio emissions. So the Earth is actually a source of radio waves as well. And going back to the late 1800s, when people were using telegraphs to communicate, folks were hearing noises that whistle. And I'll talk a little bit more about these, but these are due to lightning emissions that travel out beyond the Earth's atmosphere into the magnetosphere and get ducted by the magnetic field of the Earth and propagate over very long distances and are heard in the other hemisphere as these dispersed signals. It wasn't until 1919 that really the first scientific paper described these. So that was Barkhausen, commemorated here. He's a German physicist. He's got his own stamp. And he was a pioneer in magnetic measurements. And then it really wasn't until 1933 that the aurora was found to be a source of radio waves as well. So again, all of this is relatively recent history, and much more activity happened in the late 50s with the International Geophysical Year, and I guess, as they say, the rest is history. So just to note a few things about some of these sources I've been talking about here, so Sun, Jupiter and the Earth, they all have sort of similarities in some of the emission mechanisms that are responsible. Now, you're probably all familiar with thermal radiation, so that's just basically the black body radiation that's emitted by a warm body. The sun is a source of radiation across a wide spectrum from black body radiation. The little plot there shows this characteristic curve. But way up in the radio end of the spectrum, the sun is actually a source of thermal emission. If you've got a sensitive enough telescope, you can actually measure the sun as a thermal source, as you can the moon, the planets, at quite high frequencies, but these objects are sources of just thermal radiation. But in the case of the topics for tonight, they actually produce much brighter radiation due to other mechanisms. And one of the ones that is quite important is synchrotron radiation. So this is where energetic electrons are spiraling around a magnetic field. Because they're accelerating, they're emitting radiation. This is what's called non-thermal radiation, and quite important for the Sun, Jupiter and the Earth as well. Third type of radiation emits radio waves is this plasma radiation. So that's where you have a stream of electrons that gets bunched up, and there are interactions between the radiation emitted by the fact that electrons are accelerated with ions that are in the stream of plasma. It's kind of a wave that's generated in the distribution of the plasma, a bit like wind blowing over water to some extent. And this is quite an important source of radiation for the sun. And then finally, the other important one is what's called cyclotron maser radiation, which are very brief but very bright bursts of radiation, which is akin to this plasma radiation. It's an effect of particles interacting with radiation in a magnetic field. So we'll talk a little bit about some of these aspects in a few different contexts. So just to give you a few numbers, always like numbers, the plasma frequency. So when you've got a stream of plasma, it will emit radiation at a natural frequency, and this is related to the electron density. And this relationship here holds for all sorts of plasmas, and in fact it's one of the key little equations that radio astronomers, amateur or professional, kind of use to get something interesting out of their observations. So I guess that's the thing that really interests me. It's not so much actually observing some phenomena, it's actually trying to understand the physical processes that are happening and getting some numbers out. Now, with the sun, of course, you know that the solar corona is an extended plasma, and the density of that plasma drops off with distance from the sun. And as it turns out, the natural frequencies at which the corona emits plasma radiation changes with distance from the sun. And so if you're observing some radio bursts from the plasma process at around about 1 solar radius beyond the limb of the sun, you're looking at frequencies of around 10 megahertz. And if you're looking at 10 solar radii, this changes down to about 1 megahertz. So the frequency that you're looking at tells you something about the distance from the sun that this radiation is being emitted. Another important number is what's called the electron cyclotron frequency. So that's the natural frequency. I've talked about those electrons spiraling in a magnetic field. That's the natural frequency they'll emit radiation. It depends on the strength of the magnetic field. So if you're seeing electron cyclotron emission, you can tell something about the magnetic field strength, and that was actually used to determine the magnetic field strength of Jupiter from early observations. To give you some idea of some numbers there, above sunspots, the solar magnetic field is quite strong. This is 2.5 to 4 kilogauss, so thousands of gauss. Very high frequencies emitted from this cyclotron emission. More generally, the solar field is much weaker, and frequencies around 28 megahertz are seen. So this gives you some idea that when you're seeing emissions of these frequencies, and you're able to determine something about the magnetic field strength in these regions. For Jupiter, Jupiter's field is actually fairly strong even compared to the sun, and the radiation's around 12 megahertz, which is again in the shortwave band, and the Earth itself, the electron cyclotron frequency is around about 1.6 megahertz, and most of that radiation is actually blocked from being seen at the ground by the ionosphere. We'll come back to that shortly. Another important topic or term is this time bandwidth product. So the uncertainty principle tells us that if you have an emission of radiation, a narrow band emission of radiation, it has a minimum time over which it can be emitted. And you can use this to determine something about the characteristics of the source region. So I've put here, if we have a burst of radiation that's emitted over 1 microsecond, then the range of frequencies it can contain has to be less than about 2.5 megahertz. So this is a universal thing that holds for all radiation. So it kind of limits the space that you need to look if you're looking for certain types of radio bursts. I've got another example here. If you've got a burst of energy extending over 10 kilohertz, so a fairly narrow range of frequencies, then its maximum duration is less than 25 milliseconds. So this is kind of an interesting aspect of, well, the laws of nature. Now, sort of to go on a little bit further, I guess, you know, astronomers, well, optical astronomers like to know how faint they can observe, and over the years we've mapped out the brightness of various sources in the solar system. And so this is a plot of the brightness, essentially, what's called the flux density of different sources as a function of frequency down here in megahertz, and reminding you that generally the ionospheric cutoff is around about a few megahertz. In Hobart, actually, generally in the winter, that's down to maybe 2 or 3 megahertz, and that's why Grote-Reber came out to Tasmania to actually study the low frequency sky. So below this limit here, pretty much everything is blocked from reaching the ground. But up here, we've got solar bursts being the brightest, so the sun's actually pretty easy to observe, particularly when it's active. Lightning in the Earth's atmosphere is very bright as well, propagating over large distances. The galaxy then comes in as the third brightest source, and Jupiter at times can actually rival the galactic emission. So this gives you a bit of a guide to how big your telescope needs to be, radio telescope, or how sensitive it needs to be in order to see these different things. So what do? Well, I muck around at home with bits of wire and stuff. But what I've tried to do is build compact antennas that are easy to set up by myself and not needing ladders, cranes, other people to help me out. So this is my backyard. I've got a variety of different types of antennas, and I guess folks are probably most familiar with the dish type antenna, like the one that's out at Cambridge. I've got a little Ozstar dish down there, which I use for looking at the galaxy at the hydrogen line. That's just a little 600 mil, and that's the sort of thing you can actually do quite easily. Repurpose your Ozstar dish and look at galactic hydrogen and be part of a network. So that's a topic for another time. You can see I've got lots of trees, and I did start off by chucking up lots of wires and being a bit like Grote-Reber. Grote had a massive array at Bothwell. He would climb poles, and I guess at the low frequencies you need big antennas essentially. You've got to get something close to a wavelength or half a wavelength. I'm operating in a range where a wavelength is maybe 10 meters, and half a wavelength, which is usually what you need to pick up something, is 5 meters. So even that's getting a bit long. But I have some more conventional types of antennas, the TV type antenna, the Yagi antenna. I've got one here for meteors. There's another one here. I've been looking at auroral radio comms. So a few folks have been bouncing their signals off auroras, another topic. But I've been doing a lot of work with a couple of different types of antennas. One's called a loop antenna. So that's this thing here. You'll have a closer look at that in a second. And something that you really can't see is what's called an Earth probe antenna, which is basically a couple of electrodes stuck in the ground, and I'm actually using the Earth as an antenna. So that's a little bit about the antennas, and we'll come back to looking at the specific ones in a second. But the rise of consumer electronics has really made a huge difference, and there are little devices now that have been developed for essentially for TV reception for folks that don't have a big TV. You can watch TV on your laptop by plugging in a small device. I've experimented with a variety of these. These are actually quite cheap. AirSpy and a few others makes down here I've listed. Retail for 100 to, I think the cheapest you can get is $25, and that's capable of looking at the sun quite easily, up to whatever you'd like to pay. Basically, these devices take an input from an antenna, and then you connect that to your computer, and you can display a spectrum of the radio emission. In this case here, this is what's called SDR Sharp software, and it's showing you here what's called a waterfall display, frequency across the horizontal axis and time running down that way. It's like water falling down through a waterfall, and in this case here, this is looking in the shortwave band at some of the shortwave stations. when I started off, I just had a little transistor radio that I just listened into. And many years later, in fact, I would say it's probably only in the early 90s that I really started to do anything with computers. It's all chart recorders before then. But now this is just so easy, and you can get really great quantitative data. I put up here this time bandwidth product. Now this is for sampling with these software-defined radios. So they're inside them, they essentially digitize the signal that's coming in, the radio energy, chopping it up into a lot of samples, and then using the Fourier theorem to do an analysis to extract the frequencies of waves in that information. And for that, the time bandwidth product has this relationship here, so that you have to trade off time resolution for frequency resolution. So if you want to look at a very fine frequency range, you have a long integration time, essentially. If you want to look at a broad frequency range, you can do that quite quickly. And some of the solar bursts that I'm interested in are sort of millisecond timescales, and for that, you generally have a few kilohertz of bandwidth, and that kind of determines your sensitivity. So there's a whole world of looking at the sensitivities that you need. Just onto this little antenna. So this is my main antenna. It's literally, 1.5 meters on the side, easily transportable. I've taken this out to different places, stick it in the ground or on a tripod, get away from some of the interference. And it's really 4 loops of electrical domestic cable connected up to a preamplifier, and that then sends a signal via some standard Cat5 cable back to a receiver, essentially, back to one of those software-defined radios. This has got some directional sensitivity, so I can rotate it. It's got a sensitive plane along the plane of the antenna, so if I've got Jupiter coming up, I can point at Jupiter, but it's got quite a wide beam, so I don't need to adjust it too much. But with that, I can actually do some direction finding. This is the sort of display that I'll actually be showing you in a second, a few different examples. You'll hopefully not get sick of seeing some of these, but this is the type of spectrum. Now, in the earlier plot, I showed a waterfall, so the frequency running horizontally and time running downwards, but in this display here, I've got time running across this direction, frequency up here. This is an 8 megahertz chunk of the spectrum, and I'm using what's called Radio Sky Spectrograph, brilliant bit of software, and I just log stuff 24 hours a day, and I pick up all sorts of interesting things. So here, this display is color-coded, so the warmer the colors, the stronger the emission, but in here there are things like radio stations, radio transmitters. These sweeping things here are radars or ionosondes. Now, an ionosonde is a device that's used to probe the ionosphere, sends up a pulse and determines where it's being reflected from and what frequency. But everybody, and I mean everybody these days, has a radar looking over the horizon at somebody else. And that's Australia looking at all our neighbours, China looking at us, Russia looking at, it, and it's actually getting quite cluttered. And so some of these are radars actually from China that are looking at us. There are other sorts of signals in here, and even a solar radio burst, a very faint one here, and we'll sort of look at these. So it's quite interesting just looking around at these things, and you can spend all your time trying to interpret some of these signals. And for me, the really interesting ones are the natural sources. So that's kind of the high frequencies, but you can also turn your computer, you could actually turn this laptop into a radio telescope for low frequencies. And I do that with perhaps a more sophisticated device than your sound card, but your sound card is capable of looking at frequencies from 0 hertz up to generally probably 24 kilohertz. And this device I'm using here actually allows me to go up to 96 kilohertz. And if you remember back to one of those earlier plots, that's way, way down below the ionospheric limit. But there are natural emissions down there that, that are interesting and that come from the Earth. So similar to the SDR Sharp, you can get some free software. I use Spectrum Lab, which is an amazing bit of kit. Again, this is a standard waterfall that radio amateurs like because it's falling down, but radio astronomers like the ones that go sideways. So here we have some radio transmitters. These are the Navy submarine communication stations way, way down. And you can look at the signals of those and look at solar flare effects, for example, in the ionosphere. I've even looked at gamma ray burst effects from these. Just onto this really simple antenna. So if you've got some wire, you can actually make a really simple what's called an Earth probe antenna. And these were developed back in the war days when stealth was important, and you could actually use this technique, which is essentially, as it shows in this diagram here, just sticking a couple of probes in the ground and then connecting it up via a transformer, oscillating transformer, to your sound card. That could be your laptop, it could be that device I showed there. Technically speaking, you really should put some lightning protection in as well, but I use this technique. I have a 100 metre or 75 metre length in the case of this plan here, north, south and east, west in the stereo sound card. And I'm listening into all sorts of things with that, lightning and other emissions. So I'd recommend that one as almost the cheapest antenna you can make. And the longer you make it, the more sensitive it is. So, onto a few examples of things. So, the sun is, as I mentioned, the source of radio waves over a wide range of wavelengths. And I've mentioned the fact that some of the emissions, the plasma emission in particular, comes from the outer layers of the sun at the lower frequency. So these are the maps of the sun at different frequencies here, 25 gigahertz, right down to, in this case here, about 24 megahertz. And now there are some amazing imaging telescopes at these low frequencies. The long wavelength array in the US, the LOFAR system in Europe, the Murchison Wide Field Array in Australia at some of the higher frequencies. And it's really been an amazing boon for understanding the sources of the radiation. The things that I'm going to talk about here, the ones that are at the lower frequency end. There's a whole zoo of types of radio emission, but in the early days they were very imaginative and called them types 1 to 5, and I'm going to talk about types 1 to 3. Type 1, brief spikes that sort of form a continuous noise. In fact, it's hard sometimes to distinguish that from some of the terrestrial or domestic noise. Type 2, slow drifting shocks, coronal mass ejections propagating through and causing cyclotron or plasma emission. And then type 3, very fast electron streams, beams of electrons producing the plasma emission. And these come from solar flare events. They could be also prominences erupting from the sun, anything that's moving plasma around. And here's an example of a type 3 burst with my system, quite bright. These things are actually pretty easy to observe. And you'll notice here a couple of interesting things. The bursts come in rapid succession here. You know, there's always a lot of variety in looking at the sun. And there's a lower limit to this extent of these bursts. And that's the ionosphere coming into play. So another interesting thing is that if you want to observe solar radio bursts, it depends on the time of day as well, because if you're looking at the sun as it's rising, you're looking through the ionosphere, thick layer, which is just attenuating the radio signals. And this relationship here tells you something about the frequency, the lower frequency that you can observe. This parameter here, FOF2, is what's called the ionospheric critical frequency, which is measured by those ionosondes. And there's one down here at the Lee. The data is available online. You can go and look up what the FOF2 value is for Hobart at any particular time. That gives you some guidance on what the lower limit that you might observe. So generally, at the moment, I can observe down to a few megahertz, about 5 megahertz during the daytime, around noon, and in the afternoons, that moves up to about sort of 15 to 20 megahertz. Now, just a few examples of some of these things. You can see I'm actually getting quite good signal to noise on these, and this is that loop antenna. So that's really just this thing sitting out there in the open. And the thing that's interesting for me, it's not so much the sort of more extended emission, but I get fascinated by the really small, brief bursts of energy. And I've been working towards trying to get some really high resolution measurements of that. Still a work in progress, but these are some examples of type 2 and type 3 emissions fairly recently. Yeah. Yes. So there's one there, for example. This is one of the little things you run into. You run into your own interference. So computers are a good source of noise, and your neighbour's computer, and your neighbour's TV. And there are some of these that produce nice constant emissions. There are ways of filtering them out too, but luckily they don't spread over much of a range of wavelengths. So yeah, interference. Pretty much anything that's really constant tends to be local. And all these other things in here are communication stations of different sorts. A few other interesting things. So when there's a big coronal mass ejection, so loops of material thrown off the sun, you do get some quite spectacular features. And this is one quite recently, which is extended over a number of hours. A little bit hard to read some of the timescales there, but generally these are a few minutes across at different times over a few hours. And I mentioned earlier on the change of the plasma frequency with distance from the sun. So generally the bursts are drifting from high frequency to low frequency as they move out from the sun, as the plasma frequency drops off. But you can see here there are some going the other way. Some are actually starting at low frequencies and going up, and that's because they must be going back towards the sun. So with these sort of drifting patterns, you can tell something about the motion of the plasma. And this one here is quite fascinating because it's actually got an envelope around it. So it's a bunch of plasma that's both moving back towards the sun and away from the sun, probably in some of these loops. And I've been trying to visualize actually what these what these patterns are trying to tell me. But there's a bunch of stuff you can really get into trying to understand the geometries. This one, that particular type of emission is actually quite interesting because there's a paper just out about 2 weeks ago that talks about an auroral process, which is this cyclotron maser emission happening above sunspots. So this is where you get fairly strong fields, and electrons are spiraling down in this plasma. They could also be emitting that synchrotron radiation, those electrons spiraling in the field. But this study looked at the high frequency end, way up here. This is actually a few gigahertz, 1 gigahertz to 2 gigahertz, so up in the well above the TV bands. And actually a paper, surprisingly, talking about this for the first time. Well, I've been fascinated by this because, a little bit hard to see here, but this is a spectrum from the spectrograph at Learmonth in Western Australia, which the Bureau of Meteorology runs. And around this time, there are also quite a lot of emissions at the lower frequency end. And I think that some of those wispy things I've been looking at are actually related to some of these auroral emissions where you have a long duration sunspot just having material falling into it and spiraling down and then bouncing back out again, producing emissions that will descend and ascend in frequency. And you look at this one close up, there's emissions going both ways, drifting both ways, and it's to do with this sort of bouncing. And there could be another sunspot. Sunspots do come in pairs, different polarities, and it could be material bouncing between, but lasting many hours or even days. Rightio, that's the Sun. On to Jupiter. Now, Jupiter's a really fascinating planet, of course. Massive magnetic field. It has the volcanic moon Io throwing out plasma, and basically it's emitting radio waves by this cyclotron maser instability, one of those processes I mentioned, really bright emissions where you have electrons spiraling down the field lines but interacting with the material that's in the vicinity and producing radio emissions. And generally the emission is beamed, so these beams sweep across the Earth at times, and there are more favourable times depending on the location of Io in its orbit. Actually, in this little plot here, which is a Hubble auroral image of Jupiter, the spot of Io, where the plasma is streaming down into the upper atmosphere of Jupiter, causing an aurora there. And there's also this hectometric radiation, much lower frequencies, that is also produced by this plasma process due to Io. So these bursts have different characteristics. Some are very short, the S bursts. Some are actually much longer. The short ones are those really bright cyclotron maser bursts, very brief pulses. The longer duration ones are more synchrotron emission beamed, and the lanes here, as they're called, are when different spots of the cone sweep across our line of sight. And there are also some interesting dark bands that appear due to the radio waves being scattered in the interplanetary medium. So you can actually tell a lot about the environment between us and Jupiter with this. I've been trying to get better, and it's a bit like I see folks with astrophotography. You have your first image of Saturn, which is really crummy, just shows a couple of years, and then eventually you get something you can resolve, and then you're into a new league. Well, it's taken a bit of kind of fiddling around, but these might not look much, but in the background here, lots of little short and long bursts from Jupiter. And I'm using this little bit of software here called Radio Jupiter Pro, which actually tells me when to look and tells me where to look. So it will tell me something about where Jupiter is in the sky and the location of Jupiter in amongst these regions of favourable emission. So there are these areas here which relate to the position of Io in its orbit, Io A, B and C, and then there are these other regions shown here. This is a probability map of seeing radio emission. I guess the fun or the challenging thing is that even though Jupiter might be in a favourable location, sometimes you just don't see anything at all, and that's due to the volcanic activity on Io, which really modulates the brightness of these sources. So sometimes you won't see anything, and you can actually have, Jupiter in the right spot, your neighbour's TV's turned off, you're ready to go, and nothing. So it can be frustrating. There are, a whole garden of these things. Sometimes Jupiter's, just producing stuff down at low frequencies for a while. Sometimes it's producing stuff all over the place, and so that's quite an interesting challenge. Get to see some other interesting things here. So I mentioned those modulation lanes. So this is kind of the beam of radiation sweeping across us, just happened to intersect it. But there are these other little features in here, these little narrow horizontal bands which a good eye can see. And when the radiation is emitted, it gets split into two different states of polarization, where the electric or the magnetic vector of the wave has a preferred direction. And that's due to the plasma either around Jupiter or in the Earth's magnetic field. So you can still tell something about the plasma environment of Jupiter or the ionosphere by looking at the periodicity of these Faraday fringes, as they're called. There are those scintillation minima where the radio waves are interacting with the interplanetary medium. One thing I've been trying to do, there's a chap in the US, has the call sign K4LED. He's in Georgia. We get about 3 hours of overlap with Jupiter. For me, it's rising. For him, it's setting. He's got a YouTube channel. He streams his Jupiter stuff online. You can go and have a look at that. He's got, and I'm glad to see this, he's got exactly the same interference problems I have. I'm not alone. He's got heat pumps and all sorts of things happening. But the observation that I have here, it's hard to see on here his observation, but there are some common things and there are some differences. So this is kind of one of the still open areas of Jupiter research, is actually some of the fine details about how the emission is beamed. Right, moving on to the last kind of topic, major topic here, the Earth. And I've been looking at some of the emissions that actually do make it out into space. That's the other thing I didn't say here, that I'm really looking at stuff where radio waves have gone beyond the Earth's atmosphere and have come back. In this case here, I'm looking at lightning effects. So this is what's called a whistler, and I'll play you a whistler sound in a second. But we have a lightning storm sending out radio energy that gets out of the ionosphere, travels around the Earth's magnetic field lines in the magnetosphere in ducts. So there are plasma ducts, generally when the Earth's magnetic field is active, and these waves interact with the plasma and produce these dispersed radio signals, which sound like this, hopefully. Maybe not. Yeah. Might have to take off my laser pointer. It's descending. Yeah, so there some I recorded at home with that ground antenna, so those probes in the ground, the other little clicks there, just other lightning happening somewhere. You don't often see these. They're moderately hard to observe, and as it turns out, you can observe them sometimes when we have thunderstorms in the local area. The energy will couple into the field, go to the other hemisphere, and bounce back, and then come back to us. Or if there is a lightning storm up in the conjugate region, so magnetic mirror point, which is actually in the Kamchatka region of Siberia, and with there are a couple of sources of information. You can actually go and look at worldwide lightning activity and work out if there's something in the area of Kamchatka. I get excited because then I can go and look for whistlers. But it's interesting because in that region there's a lot of active volcanoes, and sometimes they'll produce volcanic lightning, and we'll get storms of these whistlers. So kind of fun to observe, but I guess the question is, what can you do with them? So it turns out that the Astronomical Society of Victoria is interested in them as well, and they have a station at Heathcote north of Melbourne, and their data is online, and I've been comparing my observations. So here we have a couple of whistlers at Heathcote, here, Whistler 1 and 2. I only observed Whistler 2 at Hobart, and I've overlaid these two data sets to show you that they, my Whistler sits right over the top of Whistler 2 there. So these ducts are fairly small. So by looking at separated sites, you can actually tell something about the size of these ducts, and that's not another area that's still open in research. The properties of these whistlers tell you something about the integrated electron density around the duct. So as the radio wave propagates, it gets dispersed in this plasma by what's called the dispersion law. And so what I've done here is I've digitized this little whistler here, and this is the dispersion relationship here, square of the time after some time zero is related to this, what's called the dispersion constant divided by the frequency. So if you plot this up, this relationship here, you get a nice straight line. The slope tells you something about this dispersion constant here, 70.2 per root second, which is quite an interesting number. But this number is proportional to the electron density, and you can work out the electron density around the magnetosphere. So the folks at ASV contribute to a network, and they've been looking at these things, and I'm hoping to get involved in that and look at some of the differences between two common sites. Just recently there was this amazing storm of whistlers and other things. So what I've got here is this is that audio spectrum from that little device, that audio device. I've got two chunks of it here. So I've got frequencies that run from 0 to about 18 kilohertz. I've got one version on the top here which has actually had a lot of the lightning impulses filtered out digitally. And you can see that there's this kind of storm of emission, a bit like a solar radio burst, much easier to see than in amongst all of the lightning. And these are a bunch of whistlers and other phenomena happening during a magnetic storm. The upper limit here is related to the electron cyclotron frequency. Now, I talked about that for the ionosphere, that's about 1.6 megahertz at Hobart, but out in the magnetosphere where those Whistler waves are actually interacting with the plasma, out at about 2.9 Earth radii for Hobart, the cyclotron frequency is 32 kilohertz, and as it turns out, the upper limit that you see whistlers to is exactly half that frequency. That's related to a Doppler shift. So you can tell something about, you can go backwards. If you see an upper limit to this emission, you can tell something about where it's occurring, how many Earth radii out if you know the Earth's magnetic field strength, or you can work out something about the Earth's magnetic field strength out in the magnetosphere. So a number of sort of interesting things you can get out of it. Let's go back. Some other interesting things, there are these things called hooks. These aren't necessarily lightning emissions, but they're actually some of these plasma wave effects, this maser instability producing other emissions out in the Earth's magnetic environment. And there's a whistler in there, but there are lots of these things. They're quite interesting in their own right. Sometimes you actually see whistlers that just go bouncing backwards and forwards between the hemispheres. And here's one that actually made 4 or 5 different bounces. So here's the first whistler there, and then very faintly in the background it gets further and further dispersed. I've got a sort of a lower resolution version of that here. But it's quite amazing that how just even getting a small amount of energy, the ionosphere at each end is actually quite like a mirror. It just leaks out a little bit and can sustain multiple hops. The transit time here is around about, I think it's about 1.2 seconds between the hemispheres. And from that, from the fact that you're getting these bounces, there's a relationship between the bounce period and the energy of the electrons that are out in the equatorial region. And so by measuring the bounce period, which actually it's actually around about 2 seconds here, you can limit the range of energies of those electrons. It depends on what's called the pitch angle, which is the angle that the essentially that helical path is making with the normal to the propagation direction. So there is, some ambiguity, but it gives you a range of electron energies, a few keV, which is typical of auroral acceleration. And then kind of finally, there are some other interesting features, a bit different. The hooks kind of bend over. Sometimes you get these what are called risers, which are little features popping up from the floor or even higher up. These aren't the neighbour's washing machine, but they're actually emissions due to pulsating aurora, which are putting in bursts of electrons in the equatorial region and causing this interaction with the plasma, which produces waves, which then travel to the other hemisphere and then leak out through the ionosphere. So here are some of these little risers in here that come in groups. You can kind of see a bit of a group there, another group over here, and that's relating to pulsating aurora. So you'll see that post-midnight. So I've been out with my camera, trying to look for pulsating aurora, and then trying to link up some of these things. And then finally, going on a little bit longer than I expected, but the Earth is a source of radio emissions as well, or the aurora is. Very hard to see. It's actually, the Earth's aurora is incredibly powerful. It's many megawatts of power, but it's shielded by the ionosphere. But if you're in Hobart, you have a chance of seeing it. So the aurora emits at multiples of the local electron cyclotron frequency in the ionosphere. And for Hobart, that's 1.6 megahertz. So 3.2 is twice the electron cyclotron frequency. And you've got a chance of seeing that in the winter when the ionospheric critical frequency is low. And in fact, folks like Bill Ellis, who was at the University of Reba, and others actually looked for auroral radio emissions back in the 60s, around solar minimum. And so when the sun does quieten down, and it is winter, I hope to be trying to see some of these. I guess you need an aurora at the same time, so a number of things have to line up. Okay, well, we're coming right to the end now, and I just wanted to mention a couple of things that I found quite useful that you might be interested in following up on. So there are some networks. I've kind of mentioned a little bit about, some aspects of this, but there is quite a good solar radio network called eCallisto, and the folks actually, not in Victoria, but in South Australia, the Astronomical Society of South Australia have got a station for eCallisto, and basically you can set up your own solar observatory. They've got plans and equipment. You can actually buy small kits and put together a system and be part of a network. And the good thing about sort of our longitude is that there's the only station we have is in South Australia. So if we get one in Tasmania or Victoria or somewhere, that will fill in a bit of a hole in longitude to keep a continuous watch on the sun. NASA has this Radio Jove project. Go to that website. Tells you all about how to make observations, and actually they have a database, so they do collect observations. And the folks that are using, for example, the current mission around Jupiter, somebody might remind me which one there is there at Jupiter at the moment. Juno, that's right, thanks, yeah. They have a plasma wave instrument on Juno, and the JUICE mission, Jupiter Icy Moons Explorer, will have similar. So, it's kind of interesting to look at in situ versus distant measurements. The other one that I participate in is the Society of Amateur Radio Astronomers. So that's, pay $10 a year, I think it is at the moment, US, become a member. And they've just started up in the last year a monthly Zoom chat between the US and Australia. And there are about, 5 or 6 of us now in Australia. ASV, Astronomical Society of South Australia, some folks from Sydney, and I think we've had somebody from Western Australia in, but you get to talk to a bunch of amateurs in the US. There's probably about 10 on the other side, a couple of hours on a Saturday morning. Nicely timed, 9 a.m, don't have to get up at night. And they record those, and you actually go and find those online. In fact, you'll find some of my stuff on there and listen to what the other folks are doing. Facebook's another good resource. I post a bit of stuff on some of these channels and also groups.io. So that's it, folks. So I'm still learning and doing stuff, and I'm out there now trying to build some other antennas. The one on the left here actually comes from a US array, this long wavelength array. It's an antenna about yay big. It's got dipoles, so it's got a set of receiving elements, east, west, and north, south, and you can actually then do some direction finding. It covers quite a range of those frequencies I've been talking about, so from a few megahertz up to about 50 or 60. It's a bit like that. You think, yeah, it's a bit like that. It's a bit like a bit of a Christmas tree. So it comes with a low noise amplifier. It's a bit like a loop antenna, but kind of done horizontally and tipped, and made of aluminium. And there are plans for all of these things. The folks in South Australia have one of these they've built, so I'll be mucking around. I'll try something a little bit different with my loop antenna and preamplifier that I bought. The other alternative is this one here from the LOFAR array, which is that big system now looking at the northern sky mainly. But there are a bunch of other things out there you can do, all relatively simple. You don't have to go and climb a tree, climb a tower and fall off it. You can build something on the ground, which just suits me down to the ground. So thanks very much.
Yes, Andrew, a few months ago we witnessed pulsing aurora.
Yes.
In Kingston.
Yes.
And we were in a dark cavern, and we could actually hear a humming sound. So, and other people have said that they heard it. So would that be sort of a sub-harmonic to get so low?
Yeah, audible auroras still are a bit controversial, I'd say, generally. In fact, I can remember standing out in my backyard in Glenorchy saying exactly the same thing. But being in the Antarctic, I've never heard anything there. But they do say that with a combination of humidity in the air and varying electric fields, it could create like a piezoelectric effect that makes an audible sound. But still, I think it's still not certain whether there is that real effect, because people have been out there with microphones trying to measure these things as well, or other devices. So, yeah.
This is a very strong aurora. It's pulsing.
Yes.
You can see the red colours high up in the sky.
That's right. That pulsating aurora does wiggle the magnetic field lines right down to the ground. So they potentially could move charges around and produce something. Or I think the other explanation is that even the hairs in your ear might be vibrating in relation to the changing electric fields. But yeah, open area. Encourage folks to get out there and measure it, and yeah, that's right. That's the one.
I'm amazed, Andrew, at how you manage, with all the background stuff, how you manage to sort out the integrity of particular signals when you've got interference from all sorts of domestic but also it's amazing the amount of stuff you got there.
Yeah, well, you kind of get to know your neighbours' habits, like when the washing machine goes on, and
I mean, those straight line things are obvious, but there's other stuff there that must be hard to discern.
well, I didn't show you an example there of the new scourge, which is the plastic welders and the laminating machine. So if you've got at home, everybody at home has one of these, laminating machines for putting taking the air out of your food and sticking it in the fridge. When you close the lid on those, they produce a little blip that looks just like a hook at those low frequencies. And I can see now, during the day, you can kind of track when Japan, Korea, China are doing their but plastic welding. So people that are making these fish farms, they use a welder which produces a high frequency arc that emits, and anything producing an arc like a welder is over a large range of wavelengths. But there are things that do look suspiciously natural, so it's actually getting quite hard to discern them. But generally, most of the things have been discovered, but there's still probably things out there we don't know about. Yes. Yes. Well, actually, when I was doing my PhD, we actually looked for one of the, we were trying to be the first to observe it, but we didn't have enough sensitivity. That was with the low frequency array, or actually it was the VHF array at Lanherne, which was a big paddock of antennas. And somebody thought that there was going to be a repeating source, N49, in the Large Magellanic Cloud. We looked for that, but we didn't see anything. But we put some limits on how bright that was. Now, that one's actually not a repeating fast burst source. It may have burst, but we don't know. But now the amateur astronomers are getting into it. And in the Sarah group, there's a couple of people who have actually been monitoring fast radio bursts. And actually, they're actually monitoring some of the repeaters. And they've got, one guy's got a 10-metre radio telescope that he uses to look at FRBs, and all of the processing stuff, all of these software-defined radios and all of the free software, just amazing. Pulsars, they're right into it. One guy's, he was telling me on the weekend, I think they've got sort of 30-odd pulsars they've observed with small dishes, so yeah, it's really happening out there. G'day. I see. Yes. Very much so, yes. And in fact, in that radio astronomy group on Facebook, there are a bunch of people that do amazing things with interferometers, looking at the smaller sources you can imagine. The Crab Nebula, for example, is just really a piece of cake for them. So they're off looking at little maser sources and other things now, doing the stuff that the professionals were doing 20, 30 years ago, but with smaller equipment. So yes, definitely having, even with a loop antenna, I could probably build an interferometer. That would be quite interesting. And look at the, precise direction of sources would be quite interesting. Particularly if you're looking at, say, sources of radiation from the ionosphere. There's a lot of scatter, but that might even be interesting in its own right.
Well, I like that comment of yours about things being low and looking through the atmosphere.
Yes. Yeah. That's right. But we are lucky here in Hobart because we do have this, ionosphere that's not as dense as other places. So, yeah, that's right. Yeah. The ozone hole. Oh, the ionospheric hole. That's right. Yes. In fact, if you've been watching the SpaceX missions, the SpaceX rockets routinely create plasma depletion in the ionosphere. This is the sort of thing we did back with the space Space Shuttle, Space Lab 2 experiment. The first and only shuttle mission to abort to orbit, but that mission was one of the first Space Lab missions to do space science, and the idea was to burn the orbital manoeuvring system over Hobart, dumping water into the atmosphere and then depleting the ionosphere, allowing low frequency waves to come through. And I was very lucky to be part of that because Grote Reber was also part of that. So we had a couple of papers together with Grote, and Bill Ellis led those. But it was quite satisfying as a youngster to actually be publishing with a pioneer of radio astronomy. But yeah, that stuff still continues. In fact, there's a whole active area of plasma depletion work. And you can see the galaxy at low frequencies that you couldn't otherwise. Back in the day, we didn't know, but it was all part of the Star Wars, Ronald Reagan Star Wars program. The idea behind it was that if you wanted to shoot down a satellite, you'd send the shuttle up to deplete the ionosphere, then you'd fire your particle beam weapon through it and destroy your satellite. This mission called, if you look it up, it's called Brilliant Pebbles, which is basically a particle beam weapon. That's right. That's right. That's right. That's right. But thankfully they banned that. UN banned particle beam weapons in space, which is good. So, but yeah, I didn't know that at the time. But yeah.
All of the stuff that you do reminds me of what's happening with spectroscopy.
Yes.
Nowadays, amateurs can do spectral analysis. There's so much software available.
Yeah, yeah.
Ross is not here tonight, but Ross is That looks interesting.
Very high resolution. Yeah, well, in fact, we've been using some of that gear in the Antarctic program, just high resolution, visible near infrared spectrometers to look at molecular absorption or emission in the atmosphere. You get very high. We've got a new system actually now that it's got a cooled CCD. It can give you the temperature in the upper atmosphere in about 10 seconds. At 87 kilometres from the air glow, that kind of stuff. We've got stuff we're operating for many years that 15 minutes to half an hour, and now it's all.
I wonder if those things can actually discern, say, if you've got a multiple star, a spectroscopic environment, can you get dual spectrum? Would they have
that resolution
to pick that up?
What?
This is just for the amateur.
Yeah.
Fantastic to be able to see
Well,
that.
yeah, I mean, maybe even exoplanet transits and things like that. Yeah. Probably, but it's the same problem here. Actually, interesting way. So I've talked about spectral resolution, that time bandwidth product. So you can get really fine time resolution if you sacrifice the frequency resolution and vice versa. But you need also a lot of signal. So if you're looking at spectra, you need to collect a lot of photons because your detector has noise. So it's the same problem. That's why I'm going to one of these bigger antennas to get more signal, and then get down to those fine bursts.
The whole thing, size is everything.
That's right. Yeah, but I hope you don't need these massive antennas, or you don't need to be Grote Reber to do it these days. So.
Any more questions?
Yeah, I've got one. We were out of Mount Pleasant about a couple of weeks ago, and one of the university guys was using the radio antenna, pointing it at Mars.
Yep.
And he said he's listening to satellites and rovers going around Mars. So
yep.
Are they going to use radio antennas to communicate Mars when we eventually get?
Yeah, I think we'll have probably laser comms to Mars, to the network of, the equivalent of geosynchronous satellites around Mars. But yeah, those folks are actually looking at the effects of the plasma in the environment around Mars for at least the orbiting satellite. So that's they're tracking the frequency, they're measuring they know the Doppler shift, but there are effects due to the plasma that also affect the frequency of those signals. And that's kind of one of the key things they're looking at with that. I saw a talk about that recently at a space conference that was on. So yeah, it's amazing stuff. I mean, yeah, sensitivity of that system now. I mean, yeah, looking at a few. Well, I guess there's still fairly powerful transmitters around Mars, but that's the other exciting thing. The amateur radio folks. So if you get into amateur radio here, the group, the Radio and Electronics Association of Southern Tasmania, that meets up on the Domain. You know, they're communicating with milliwatts of energy between the hemispheres here, different frequencies. Moon bounce, I've got that one of the Yagi antennas, the TV type ones. I've been looking at the moon to pick up a radio transmitter in France. The space debris, and it's debris not as in the cheese, but the space debris or satellite tracking antenna in Graves in France is, I think it's nearly a megawatt, but it's you can actually see it reflected off the moon in Hobart. But yeah, I mean, the receivers now are really sensitive for all that kind of stuff. So, yeah.
So that one in Grave you're talking about, that is like a radar.
It's a radar. Yeah, just seeing it pulses. 143 megahertz. So that's, you know, within the amateur radio band. So
How is all this work that you're doing affected by the myriad of
well, funny you should say that, because I can actually pick up the so there's I do radio meteor stuff. So there's a transmitter in Devonport, one of the radio amateur groups runs. I've seen that bouncing off Starlink satellites back here. So it's not so much I guess I'm not looking up at the high frequencies so much, but I can actually see those satellites just through other things bouncing off them. Space station you can see as well. So they're up a few gigahertz, but you can pick them up. A little dish I've got, you know, for example, that's an Ozstar dish, which is one of the, I think it's the K-band. It uses some of the Starlink satellites are kind of up in the gigahertz range. That's got a wide bandwidth amplifier in it, and I've looked at other frequencies there. Looked at the Optus satellite out at geosynchronous orbit, and I've used that to measure rain attenuation, because at those frequencies the rain actually has an effect on signal. So there's other exciting things you can do with radio. But,
Could you pick up a supernova pattern to go off quicker than optically?
no, well, the radio waves should be travelling, well, you know, there might be a small time difference there. If it's producing that electron cyclotron maser instability, you get some really bright emissions that you might detect before a optical pulse, but they'll be coming along at the same speed. But I hope I don't see one of those, because it's probably going to be very close.
Well, Andrew, look, thanks very much. It was a fantastic talk, really interesting. And I hope we get some radio astronomers out of this in our group. Yes, we But yeah, and also spectroscopy too, which some of us are interested in, starting to get, you know, interested as well. So, all right, we might have a little break now. All right, I will just quickly do a. No, that's better. No. Oh. Good. That sounds good. Music. Oh, that's just a bit of Tchaikovsky. And that's Greg's Rasser. No, it isn't. That's a big Schmidt-Kessler. Okay, so just do a little bit of a talk on the summer sky and what's up for the next few months. So I thought I'd just quickly now, I've set this for 15th of January 2024. So roughly. So 10:30 p.m. because it's still light. So 2024, yeah. So if you look up here, this is what we're going to see for the next few months. These constellations, you've got Orion, this is the north, Orion, Monoceros, the unicorn, Gemini, Taurus, and can you all see that clearly at the back? Yeah, okay. Sorry, and of course Jupiter, which will be around for a while. Now, just a thing, over here, you'll notice Canis Minor. If you visualise the art for these things, the little dog is always on the back of the unicorn. This is how you'll find your way around the sky. So if you want to find Procyon, which is Alpha Canis Minoris, it's always the Minoris. So there's the front of the unicorn, and that's riding on the back. And up here to the right is the big dog, Canis Major with Sirius. So they're always around, the hunter and his dogs. So they're always that part of the sky. That's one way of remembering things. So anyway, we're going to look at some of these very interesting objects that are down here. Of course, the Pleiades, which I'll talk about briefly. And a beautiful thing, and that's my next photographic target. And Uranus, which is about magnitude, I don't know, Steve, help me out here, 5.7 or something? Yeah, at the limits of naked eye visibility anyway. So, and of course we've got Castor and Pollux, and Castor, wonderful 6-star system, remember that? With those blue star and then a dwarf. And in fact, the dwarf binary, the last one is 2 dwarf stars, red dwarf stars. So a beautiful system. And I think, from memory, I think it's 51 light years away. But remember those, Pollux is always the top one, Castor always the bottom one. And Pollux is, I think it's a giant, class 3 star, a bit cooler. Anyway, let's have a look at what we've got up here. A bit of a concentration on Orion. Now, you're all familiar with Orion, so what I thought I'd do is pick you out some things that you may not be familiar with. Apart from Regal, by the way, Regal is a quadruple star and possibly a quintuplet, and it's got it's a supergiant, B81A supergiant star, and its components next to it is a triple system, and the triple, when I say next to, it takes 24,000 years for the triple system and the supergiant to make a single revolution about each other, common centre of gravity, not centre of barycenter, I suppose. And those other stars are they're all the same, exactly the same spectral type, B9. And the first one is a spectroscopic binary, and then a third one, which is a 10th of an arcsecond away. So you can't always see, you can see them as pinpoint dots, but there's a fair separation. I think it's 9 arcseconds between the primary and the others, so quite a distance. Now, here's something I wanted to show you. Now, we all look at Orion Nebula, but how many of us actually look at this beautiful little cluster of stars up here called NGC 1980? That is spectacular and very bright, but we always sort of focus on Orion and forget about it. And it's a beautiful object, and the lost jewel of Orion, it's called. I won't give you the Arabic names, they're too complicated to remember. And here I've got, you probably can't read that, but that's at a 35 magnification, roughly. That's what you'd see through an eyepiece. But of course you can crank it up, and with clusters I always do because they're bright enough, inherently bright enough to use high magnification with. Alnitak, of course, and there's my old shot of, famous. You could, can you make out? No, you can't there, it's too small. The face, the spooky face right there. I can never look at that thing now without looking for the face, courtesy of a guy who gave me a massage. Anyway, the interesting thing, whenever I think of Orion, is that just about everything there is between 1,300 and 1,500 light years away. It's almost like a 2D, not a 3D type constellation. They're all part of the Barnard, what do you call it? The OB association. So all the stars come out of the same molecular cloud, etc., etc. So things are pretty much, as you see them, at the same distance. So Sigma Orionis, what an amazing, how many of us look at Sigma Orionis? We don't, we just get annoyed because it's one of the bright patches shots of the Horsehead, but it's a multiple star. And in fact, that one, the middle one there, AB, that's a triple system. So you've got a spectroscopic binary and then a B component, all super, this one here is a giant star, supergiant star. And then you've got over here, if I can just show you, get this going. Yeah, Sigma Orionis. So this is the star that lights up. You can see it's a multiple star. You can see it even through a pair of binoculars. Down here, you can see all of this ionisation here is caused by that particular group of stars. And it's actually part of a bigger cluster. So it's hard to separate these from the rest of the cluster. They're all pretty, there's a lot of stars in there. Now over here is the thing that I thought, now I've done this so that I took two different systems here. One is for observers, one is for photographers. Now this is a photographer's dream. It's one of my new, this is M78, you might recognise it. It's not very far, Messier 78, from a reflection, largely a reflection nebula. It's found in small telescopes, a hazy patch, 8x6 arc minutes. So you can actually see it, but you won't see any detail or anything. You obviously need a much larger instrument to see anything at all, really. But photographically, it's very interesting. Now that one there is at, how many magnifications? 35 magnifications. So that's what you'd see if you could see much. Use low magnification for these things to get the brightness if you want to pick up some of the nebulosity. Now that's, I've framed that with my, I can't see. I think maybe I wrote it down. Oh, yes, I did. Good boy. So that's with my big APM telescope, but that doesn't matter. It's the magnifications, the scale, picture scale, and it's 1 degree 7 minutes by 44 minutes. 44 minutes of so you can fill the frame. So those of you who've got Schmidt Cassegrains will find this a wonderful target for the summer sky. Moving on to Taurus, beautiful Taurus. We all recognise this little thing up here. Quiz. What is this V-shaped object of stars called? Hyades, thank you. I was also getting me worried. The Hyades. Now, Ulysses, the poem Ulysses by Alfred Lord Tennyson. Remember that? I don't know if you know that poem, my favourite poem in the English language. When the rainy Hyades vex the dim sea, because they're associated with rain in the northern hemisphere, and the Pleiades too. They're all sisters, by the way. So the Pleiades down here, or the Subaru as the Japanese call them. Hang on, sorry, I've mentioned Uranus before. I wouldn't hold your breath too much if you're looking at Uranus. That's a very high, that's 470 magnifications. It's not a big thing to see. It's too far away, 84 years to go around the sun. I believe it has a greenish blue hue, Steve. You've been observing it a lot. Yeah. But anyway, moving on. So, this is interesting. Aldebaran, the star you see there, which is about 65 light years away, has nothing to do, that's a giant star, has nothing to do with the Hyades, even though it appears to be. The Hyades, the V shape there, Theta, Iota, and all of those are all giants. They've left the main sequence. The old stars that are going through the red giant phase, they are collectively a group. They belong to each other and all moving in the same direction. Same, clusters do that till they break apart. So they're all moving in the same direction. And so this is a beautiful object to look at. And the father of these girls is the same daddy as the Pleiades, Atlas, or so they say. If you read about the mythology, they're all different. They've got different solutions to who was the father and who was the mother. But in this particular group, the Pleiades, M45, which, by the way, is the closest Messier object to us. I don't know if you knew that, but it is 444 light years away, and a bit. I think the Hyades are older, yeah, than the Pleiades by quite a bit. And in fact, the Hyades have got a 330 arc minutes across, something like that, which is a lot. That's 5 degrees, 5.5 degrees. It's quite a spread. But Steve and I at Rathmore House looked at the Pleiades. I could not believe it under a Bortle 2 sky. They were like search beams. They were so bright. You couldn't miss them. They were startlingly bright. I looked up and thought, God, yeah, an amazing object. We looked through Steve's 5-inch fixer and it was just spectacular. It's absolutely spectacular. So we are missing out a bit on our, unfortunately, on our skies. And out at Mount Pleasant, I think we've got a Bortle 4, I reckon. Looks like a Bortle 4 somewhere around there. So we are missing out on some of the really dark skies. But anyway, what a wonderful target. You know the Japanese call it the Subaru, hence Subaru. I think we've done this before, talked about it. Perfect match for a particular, I wanted to show you the two together, the Hyades at the top and the Pleiades. This is the correct orientation for down here in the same field. That's wide field. Over here, on the right-hand side, M35. Now, you might know about this cluster. Very pretty little cluster through an eyepiece, and there's another cluster near it. The one in the foreground, 418 stars, 2,970 light years away. M35, very pretty as you can see. Now that picture there, I've got it at 70 magnifications. So if you're looking at clusters, I think 70 to 100 is about ideal. 70 to 100 magnifications because they're just bright. And that's quite a bright cluster. But that one there has nothing to do with it. And in fact, it's so far away, it's, if you look at the distance, 2 billion years old and 11,000 light years plus away. So it's a bit like looking at those two nebula in the Statue of Liberty Nebula and the one in the background, which is the biggest emission nebula in the galaxy, and that's 20-something thousand light years away, and the Statue of Liberty is 9,000. But they look like they're connected. You know, hard to tell with gas, of course, being so diffuse and everything to measure distances accurately. So, yeah, there you go. Another big picture. I've got a bit besotted with that. It's going to be an interesting target to look at through an eyepiece. Now, the Flaming Star Nebula. I bought this for you, Eugen. This is especially one I know we're going to, some of us will be imaging this. I didn't realise this existed until I was looking at it. I thought, what is that? You know, you look at, you open Stellar and you think, what's that little red patch? And there it is. It's the thing on the left there. This is the Flaming Star. I don't know what that is there, but a worthy target for a camera, I think. This one, IC405, 50 by 30 arc minutes. It's massive. That's almost 2 moon widths. So, yeah, in Auriga. So Auriga's got all these other things, like down here. Does anyone know what that is down there? Greg England would know. See down here, little red thing there? That's the California Nebula. So Auriga's low down on the northern horizon. It's a bottom, virtually hitting the ground. And so there are some very interesting targets in there to look at. And there's an amateur picture of it, not a bad picture. Yeah. One of the cameras that I'm impressed with is something we know and we never buy anymore, is the ASI 1600 mm. Yeah, and it has the most beautiful, all the pictures I've seen of it just so fine. They're the monochrome version of that camera. I don't think there was ever a colour version. But was there? There was a colour. Because I remember Ian Woodward had one, and the pictures, the beautiful, the stars and the resolution was excellent. Yeah. Mm. All right, looking east. What can you see in the east? Well, you've got Canis Minor over here, Monoceros, and over here, I'll come to that in a moment. Anyway, gee, this looks gaudy up here. That looks a bit different. Let's have a look at a few things. At the top is Canis Major. And over here on the left is this little nebula. I don't know if you've done this one, Eugen. It's called Drea's Nebula. No? Fairly small by the look of it, but there are lots of amateur photos of it. And it's got a reflection, and the red to the right is the red from the Cone and Fox Fir Nebula. And that image is actually, you have to turn it upside down, leftward, 180 degrees to the left. Sorry, not 180, 90 degrees to the left to get the correct orientation. So, yeah. No. So the antler triband might show that. Yeah, yeah. Yep. So there you go. There's a close up of it. These are the sorts of things, Lisa, for the celestrons. And that's a picture with again with the APM, I think, filling the frame. That's 1200 mil focal length, to give you an idea. So a 1 degree field, something like that. Dreas Nebula. Anyway, I just thought I'd introduce that. Now there's my old shot of the Rosette Nebula, which is up here. So all of these are straight under Monoceros. So all of these are part of Monoceros around here, within close proximity. And you've got, of course, by the way, that's quite bright, isn't it? Mind you, you've got to remember, when I say magnitude 4.8, it's an integrated sort of thing, like comparing it to a star, reducing it all to a star, but it doesn't work that way. It's diffuse, so it's a lot fainter. You'd have trouble, but still worth looking at. So Christmas tree cluster with cone and foxfir, another target I want to do properly. And there's a wide sort of field view of that area, the cone and foxfir. If you look down here, you can see the cone nebula there, a foxfir coming in here, and at the top, or sorry, not the top, here, see that bright star there? That forms the base or the trunk of the Christmas tree. See the triangle? That's a Christmas tree. Sorry, just pointed a bit slow. Yeah, so there are some things to look at in the east. Now, just looking close up for a moment at Canis Major. Sorry, yeah. Well, I didn't know where to go. So now, you know, when we look out at night and we see Canis Major, and we usually see 4 stars. We see Adhara up here, Aludra, Wezen, and then down the front, Sirius, at the pointy end of the dog. But in there are some fascinating things. If I can just show you, right next to it, down here, is the beautiful Seagull Nebula. Now, you really need wide field like a Red Cat 71, something like that to get this in, because the wings are quite broad. That is an amazing, it's 100 light years across at the wings, but it's actually, the whole extent of it is 240 light years. From top to bottom, if it were an angular measurement, I suppose, from the top of one wing to the bottom of the nebula, because it's so diffuse. It's amazing. I'm going to show you another image of that shortly. And so that's where that is. And there's a picture using I think that's the William Optics. So that's a 100 mil telescope with a field of almost, I think it's close to 2 degrees by 1.5 degrees. So it's still not enough, obviously. So there's one. Now, this beautiful, beautiful cluster of stars, M41, the little beehive, worth looking at. That's a binocular view of it. It looks tiny, but that's to show you the minimal sort of size of it. And there's a lovely picture of it. Beautiful, beautiful cluster of stars to look at. So if you're keen on observing. Now, over here is this group of stars that Steve introduced me to in Puppis. Now, this is NGC 2477. And electric guitar or termite hole cluster. That is amazing to look at through a telescope. It is stupefyingly pretty. You look at it and you think it's sort of like a denser version of the wishing well, a more concentrated form of the wishing well. It is amazing to look at. That's a picture I took, it's only a tiny version, 27.5 minutes, so almost a full moon in width. Beautiful, magnitude 5.8. There's a close-up view at 100. Cool. Oh yes, and Burnham loved it too. Robert Burnham and other people. Celestial Handbook. One of the top open clusters in the sky, and there it is. There. What's the magnification? 140. I'd do it because it's so bright. The central concentration is so bright. It'd be worth cranking up the magnification a bit if you're interested. So there's a beautiful cluster. Now down here, not far away, is NGC 2547. Called the Golden Earring. I don't know how you see a golden earring. St. Peter's Cross or Malus cluster. Seems incongruous. St. Peter's, holy, Malus, the Latin word for evil, wicked. So I was looking at that and thinking, oh, that's interesting. Anyway, 85 magnifications. So there you go. That's a pretty cluster as well. Let's move on. So you've got some interesting things there in that part of the sky. Isn't that spectacular? Is this a Hubble image? I tell you, the seagull, in all its glory, just taken a week ago by our friend, Eugen. Look at that, isn't that beautiful? That's a wonderful image, taken with and the L extreme, or the F2 version of the L extreme. So there's a new version of the L extreme, which is only hydrogen alpha light, but it's very, it's even.
Yeah, the window is narrow. The L extreme down is past that is 5 nanometers, so the L is 3, I think.
Gee.
And it controls the halo.
Yeah, that's what we the halos around stars. Yeah, what a beautiful image, Eugen. I think that's terrific. A nice one to put on the wall.
You missed a couple of very nice objects in dense nature.
Oh yeah, I know. Like the
Horse helmet.
yeah, and the blue dolphin. Yeah, I know. I didn't want to go through all the yeah.
There are a couple more.
Yes, I saw that down the bottom. Yep, I saw all of those. Yep, but I didn't want to pack this up with too many.
The spotted crossbones, that looks really,
Oh,
really
right. Well, here we're looking at south, and I've magnified the Southern Cross area because you know all these things down here, of course. However, a couple of things to look at. Remember the beautiful Capacrucus NGC 4755. Up here, the wonderful running chicken. Now, a group of kids, where were we? They loved the running chicken. Girl Guides. The Girl Guides at the Lee a few weeks ago. They all got the giggles. I couldn't believe there was a running chicken, but there is a running chicken. So that's IC 2944. I don't know how bright that would be in a telescope. It'd be very diffuse. You can't see it. It's hydrogen anyway, so won't see it. Yeah. But you need a wide, slightly. Sorry, Steve. No. Yes. Yep. And we've got here a very familiar one. Anyone know what that one is right next to it? 3766. Anyone remember what this is? Gem cluster? Pearl cluster. Pearl. The Pearl cluster. A rival to Capacrucus cluster or jewel box. And up here, this is wonderful to explore. Binoculars, anything. There's my shot of the Statue of Liberty. Now that's that nebula I was telling you about in the background. That's 20,000 light years away. And it looks like it's seamlessly joined to this one, which is the Statue of Liberty, which is only 9,000 odd light years away only. Anyway, so down here, so above that, you've got the beautiful Wishing Well cluster or Black Arrow cluster or Football cluster. I think it's got all these different names. But through an eyepiece, this is a dazzler and well worth looking at any magnification. And it does look like you're looking into a wishing well with silver coins in it. You can't see the colour, you can in my photo of it, but you can, and you can't pick up the nebulosity, but you can, the stars in it. And don't forget, it's got 7 red giants and 7 white dwarves in it, which I think is hilarious. This is the stuff of fairy tales. Anyway, a beautiful cluster to look at, well worth looking at. I'm just picking up things. Here's my shot of Eta Carinae. I mean, that looks spectacular in any sort of telescope. And you can see all sorts of things. Just beautiful to look at and to take photos of. Now, we're nearing the end. You might remember, I took this photo. Everyone remember what this is called? The Gabriela Mistral Nebula. Now, she was a Chilean poet who won the Nobel Prize. And I think in my presentation there, I superimposed her face, her profile, because it fitted this perfectly. There's a nose, forehead, nose, mouth, chin, rounded face. Anyway, I don't know who thought of that. Someone must have, that looks like Gabriela Mistral. Anyway, but the reason I've shown you this is this beautiful cluster of stars here, which at 100 magnifications is just spectacular. This is the gem cluster, and I think this gets the gold medal out of all of them. The Capacrucus, the Pearl cluster, this one is beautiful. It's a bubble, yeah. Oh.
Right there, difficult to
Yeah.
see, but if you image that area, you'll get it.
Oh,
Yeah, it looks like the bubble there.
just like the bubble. By the way, if you look up here at the twirly whirlies, can you guess where this is? If I turn that 90 degrees to the left, that's Eta Carinae down here. So it's in that top section of Eta Carinae. It's very close. It's part of Eta Carinae. It's just to the top right of it. So if you're looking for this, it's a beautiful little cluster, just beautiful. Anyway, there's a Hubble image. ESO, I think, 2.2 metre telescope image of that cluster. Billions of dollars. Man, you know, $3 or $4 grand. You know, you don't need to spend a fortune. Anyway, 3293, yeah, the Gem cluster. And there's I forget what size, I think that is 100 magnifications. Yeah, that's what you'd see. Very worth looking at. Now, finally, in the west, you say, an empty sky? This can't be. But we're looking at Sculptor. You know what Sculptor means? Galaxies. Lots of galaxies. So I thought I'd show you some of the galaxies. By the way, these numbers you see are part of the list of 200 brightest galaxies. And some of the ones in Sculptor and around it are part of that list of bright galaxies. So, I mean, I guess that means surface brightness, for want of another way of putting it. You know, the surface brightness is a measure of, what is it? Magnitude per square arc second. Is that right? Yeah. So, let's have a look. Ta-da. C70, Colander 70, Caldwell 70, NGC 300, which Stellarium, as we always say, mistakenly calls the whirlpool, the southern whirlpool. It's not the southern whirlpool, but it is a bright galaxy, really quite bright. And I wouldn't mind looking at that through a decent telescope, which we've got lots of. 21.9 arc seconds across by 15.5 magnitude 9, but worth looking at. Down here, I've got one picture of that, one subframe one night where an odd angry shot I took. Just was running out of time. What's this? Let's take this thing. The String of Pearls galaxy. It is really bright. I was stunned. In a 2-minute sub, and you can see the whole thing in a single. So I'm going to take a lot more photos of that. Yeah. No. But that one there, you can see the brightness. This here, wow, that's really bright. So there's one for you folks. Number 2, 30, that's the size of the moon. Yeah, I was amazed at the size of it in the, anyway, down here, a Bond's galaxy, which was, I think it was in the news recently. I saw it somewhere, there was an article on it. Anyway, that looks like an interesting target to image as well. And over here, Caldwell 62, the Needle Eye Galaxy NGC 247. These are a few of the examples. If you get your Stellarium out, you'll probably see, of course, my my picture of Sculptor, which is 11 million light years away. And that's a bright galaxy. I mean, you know, in no time at all, you've got heaps of light coming from that. Very bright. Silver Coin Galaxy, Sculptor Galaxy. And again, about the size of the moon, so very similar in size to the String of Pearls galaxy over here on the left. And over here is this galaxy. Now, I haven't, the Giant Squid Galaxy. I don't know how they call it, giant. It kind of looks a bit like it, but it's very small, 8 arc minutes, so it's not very big. And you need a large instrument really to do that justice, probably. And over here is, in case you get bored of galaxies, there's a globular cluster. The only one I could see in that area, NGC 288, yeah, magnitude 9, binocular object, but probably be quite faint. It's not terribly bright as globulars go. And then I was going to show you something that, you know, you often think you see the galaxy on one side of the sky, the Milky Way there on the other, and you think, what's happening? You know, the actual cycle of the year and the process of rotation as we go, as the sun moves around the Milky Way, as we move around the sun. So I thought, I really like this diagram. I use it in the NSE course as well, sometimes, purely to show the angular tilt of the solar system relative to the galactic equator, which is 60-something degrees. And then this interesting thing. You notice when we're looking out at this time of year, which is, let's say it's summer, we're actually looking out away from the galaxy, out towards Orion and those. I'll show you what this means in terms of a diagram. We're traveling at 850,000 kilometres an hour or something. But when we're looking this way, this is during our summer, which is their winter. So when it's our summer, when it's our winter and their summer, we're on the other side, and the Milky Way is more prominent in our view for that time of year. And we see it. But once we get around this side, we're looking, during the night sky, we see more outwards. We're looking outwards. Does that make sense to everybody? I thought I'd put this in because you don't sort of think about it too often, but you think, why is it, you can see it's sort of sparse. That part of the sky is sparse for nebulosity and everything else because you're looking well away from the galaxy, of course. Now, this diagram is the best diagram I have seen on a galaxy anywhere. I've combed the internet. This is really well done. And because down here, it gives you the position of the sun and these sort of like azimuth orientations, east, west, north, south. But down here, if you look, just down the bottom here, it's got all the constellations that we're looking at the moment. Orion, Taurus. So we're looking, you can see we are looking out and not towards the centre. So it's a two-dimensional way of showing what I was just talking about in the last slide. And of course, up here, you think, all right, so you see this line here, the dotted line, right? And this dotted line, they represent the shadow. We can't see the other side of the galaxy. However, what are all these NGC figures here? What are these? They're all globular clusters because they're not on the galactic equator, they're miles above it. And so down the bottom here is a diagram showing you the scattering of globular clusters, which is why we see so many of them, because they're easier to map because they're not on the galactic plane, and they're visible because they're above that dark shadow area, if you like, or the invisible area, part that we can't see. And then I think we're the last slide. In their endless quests for nirvana across the heavens, astronomers face, I've made this up, many earthly perils. Cold, excessive consumption of party pies, life-threatening cable snags and headlong falls into tripods and telescopes, which we have experienced. Relentless attacks from out-of-season mosquitoes, which we do have. And of course, the blinding car headlights of gormless neophytes, momentarily forgetful of observing protocols. I had to say that because I'm one of them. But nothing can prepare the dedicated observer for the fatal consequences of too much time spent at the eyepiece. That's the sound of astronomers disappearing. I love Gary Larson. And there's always, have you seen that one? Look, I love it. There's a lady in there cleaning his office. And Einstein is at a whiteboard. He's got E equals MC cubed, E equals MC to the 6th power, all this stuff. And she says, yes, sir, all squared away. She's cleaning it. He's got this look on his face. MC squared. Anyway, I love Larson's cartoons. So that was a quick little Cook's tour of the summer sky. But there's a lot of interesting stuff. And as Eugene was saying, over in Canis Major in that area, you've got the Monkey Head Nebula, all that stuff down below. It's fairly low, but it's still good enough to take pictures of a jellyfish, which looks like it's a weird thing. Looks like a translucent brain. It looks really strange, yeah. Oh, yeah. Oh, yes. That is an amazing little scope. Have you seen those, Andrew? ZWO have made them, make cameras, they automated. Yeah. Oh, the little kids, oh, gee, I wish we'd, that's a, well, we could look at those. Let's, hang on. Yes, I think so. Let's close that off. Okay, out, yeah. Pop that in here. There we go. Ta-da. Yep. So have you got the times for these, Lisa?
Yeah, they're all only, that's 2 minutes. So it's NGC 104, copy your customer.
Yep. It looks like 47 tuck, is it? Or?
Yeah.
Yeah.
That's the Lagoon Nebula. That's with the filter on it, so it's quite a bit darker.
Yeah.
Sorry.
That's a butterfly, M6.
Yeah, that's M6.
Yeah.
And that was only 1 minute.
Gee.
Helix, that's 3 minutes on the helix.
3 minutes.
Yeah, so it stacks 10-second exposures.
Right.
And this is straight from the app. These are just JPEGs. I haven't touched them.
No.
Just put them straight off the device. That's Edicar.
Yeah. Gee, the dark dust lanes are prominent in that.
Yeah.
Fantastic.
So, but I mean, if you spend a bit of time, a bit of quality
You could do it.
time on something.
Yeah.
Moon.
Moon. Orion Nebula and the Running Man, yeah. And the Flame.
I mean, that's 4 minutes. That's a bit.
Oh.
N79.
Is that the string of pearls?
Yeah,
It looks
that's
like
the
it.
string of pearls.
NGC 55, folks. So,
Now, this was what I was trying to email you, the Jack Bennett catalogue. So this is an object, it's a little galaxy, and I'm going to put the big scope on this one.
Yeah.
Because that's got some
It's
beautiful...
wave. It's got a wave.
Beautiful spiral.
Yeah, you can see it's got a, you know, when they get that warped, yeah.
Yeah. So that's, I thought that's pretty good, and that's the comet.
Oh, right.
Yeah. C2023H2 Le Monde.
Le Monde.
And it was through some clouds. I mean, I had a lot
Yeah.
of clouds, but, you know, I mean, comet hunting was one of the first things I did when I started getting into it.
Yeah.
So that was kind of cool. And it literally, you just stick it on the ground,
Yeah.
2 seconds to level it, and away you go.
Amazing,
It's
isn't it?
so simple to use. So
And the
easy.
kids love seeing it, yeah.
And so I did all of these while the big scope's working away on
Yeah.
whatever.
Yeah.
Oh, yeah, or comments, or
Yeah.
who knows? I think it's a great
Beautiful.
thing.
Look how sensitive that sensor is to pick that up. It's got the nucleus. You haven't got any the short exposures because you've got no star trails. So
Yeah.
that's picked up quite a lot in a very short. And you can
like
see.
I said, it's quite cloudy. I mean, you can see the clouds on the image.
Yeah.
You know, it's
Beautiful.
cool. It's there. You can see.
It's good fun,
and
isn't it?
It's really user friendly, and it's heaps of fun. Oh,
Yep.
I'm tickled pink with
Yep.
that. Oh, that was another comment.
Ah, yeah. What's that one?
That's on there. V2 Canstar. No, it's ZGF.
Oh,
one.
V2. 3 minutes. Jeez.
Yeah.
Ah,
But they were just the ones that were visible
Yeah.
at the time. This is on the top of that.
that's fantastic.
So anyway, so that's my little sea star. Oh, that was nice.
Oh, that's your beautiful running. Oh, I love that. That's with the C8 at last. Isn't that gorgeous?
And
That's a
I took
beautiful image.
Fornax A Galaxy, which Steve was nice enough to point me into
Yeah.
in the direction of some information.
But yeah, you were saying, oh, the stars, you know, I love them. I love stars having a bit of glow about them because that looks natural, you know. Once you reduce them to just pinpricks, they seem to lose their,
Yeah.
yeah.
Well, look, it's probably a different. I don't know. I was thinking about we all, you know, process in our own individual style, and I
Yeah.
guess I was just wondering, you know, whether this is a more feminine take, you know, like it's a bit more
Oh,
luminous.
it's lovely, beautiful. It's got a beautiful glow. It's lovely.
Anyway,
Great image.
but yeah, so the sea star is heaps of fun.
Yes.
Absolutely heaps of fun. Absolutely.
God, Andrew, I was just thinking, gone are the days when we used to. Andrew and I, by the way, got one of the first images of supernova 1987A. And it was pure, it was kind of accident, really, wasn't it, Andrew? We were looking up at the Magellanic Cloud, trying out these clockwork drives from Germany, the purest astromechanic. And we wind these things up and they turn at sidereal rate, supposedly. And I remember having a 135 lens, I think, on the LMC. And we processed, it was a gas hypersensitized Fujichrome 400 or something. There was the supernova. And the university took that and duplicated the slide. I was happy to get it back, actually, the original. I thought they could. But anyway, that was a lot of fun. So those days, oh, gee, that was a long time ago. Yeah.
The night we actually, the AST meeting, that we actually probably saw the supernova but didn't realise it.
Yeah.
What was that,
Yeah.
87?
87, yeah. It had a very orange glow on the actual slide. So I think it was a day or two old.
Yeah, well, it was actually, I think it was
February
3 hours
23rd.
old, it was about 2 hours before.
So we've got one of the earliest pictures. I've still got it on one of my old digitally converted it, but I've got it somewhere. But that was amazing. And that weird experience we had. Where did we go and see Halley's Comet? We had a workshop, you and I. Was that at and that when that little old lady who was about 90 got up on the pedestal to look through my homemade 8-inch, which Laurie and I had made, an 8-inch telescope. And I said, don't touch the telescope. She said, where is it? And I said, you're looking at Halley's Comet. She bumped the telescope and it swung around to Omega Centauri perfectly. So there was Omega Centauri detailed on the front. She said, oh, that's boring.
Jeez, back in 1910, it did look like that.
Yeah, that's right. Oh, it's just the amazing things that happen. But, you know, back in those days when we used to meet, we'd be doing those crater timings, and Stefan used to be around too, and we'd click those little frogs and say, go on, you know, you do occultations. And anyone looking in on us would think, this is a weird group of people in the dark going click, click. Nothing's changed.